Related rates of change. Sometimes we are given one rate of change and asked to find a related or connected rate of change. We can use the chain rule to find this rate of change. For example, suppose we are told that the radius of a circle, so the radius of a circle, is increasing at 5 centimeters per second, and we want to find the rate of increase of the area of a circle. So there's a very similar question to this, a very similar example to this in the Leaving Cert Ordinary Level Calculus playlist, if you want to have a look at it. Let R be the radius of the circle, so R is the radius of the circle, and let A be its area. Then we are told that the rate of change of the radius R, so with respect to time, is 5. Hence, dr dt is equal to 5 centimeters per second. So the rate of change of the radius with respect to time is 5 centimeters per second. And we want to find the rate of change of the area, A, with respect to time, i.e., that is, we want dA dt, the rate of change of the area with respect to time. We can use the chain rule as follows. So what we want is dA dt, and this is equal to dr dt multiplied by something. So this is what we were given, dr dt, and we need to now figure out what goes here. So we need to figure out what we multiply this by to get this. This is what we're looking for. So if we just focus in on the fractions, we have dr dt, so we already have the t, we already have the denominator, and we need to get a numerator of a. So if we multiply by dA over something, we'll get the dA, but what we need to multiply is dA over dr, so that this top dr will cancel. So we'll cancel out the dr's on both. So to get dA dt, we should multiply dr dt by dA dr. So this is what should go here, dA dr. So that the r in that numerator and the r in that denominator will cancel, and we'll be left with dA over dt, which is what we want. So to get dA dt, we should multiply dr dt by dA dr, because then the dr above and below, so in the numerator and the denominator, can be cancelled, leaving us with the required dA dt. Thus, dA dt is equal to dr dt multiplied by dA dr. So this was given to us in the previous slide, so I'm going to move down to here. So the first step is to calculate dA dr. So we need to work out what this is. Because remember, ultimately, this is what we're looking for, dA dt. So from the formula for the area of the circle, if A is equal to pi r squared, then dA dr is equal to 2 pi r. So we bring the power down in front, the 2 comes down in front, we reduce the power by 1. 2 minus 1 is 1, so we just have r to the power of 1, so we have 2 pi r. Now, as dr dt is equal to 5, by the chain rule, dA dt is equal to dr dt multiplied by dA dr, and dr dt is 5, and dA dr is 2 pi r. We got that up here. And 5 times 2 is 10 pi or centimeters squared per second. We can now evaluate this for any value of r, for any radius. For example, the rate of increase of the area when the radius is 2 centimeters is 10 pi times 2, which is 20 pi centimeters squared per second, and so on. Example. A liquid is poured into an inverted cone, apex down, at a rate of 3 centimeters cubed per second. So here we have a cone, and the apex is facing down, and the liquid is being poured into it. And the rate at which it's been poured in is 3 centimeters cubed per second. The cone has a radius of 20 centimeters and a height of 48 centimeters. So a radius of 20 centimeters, height of 48 centimeters. Find the rate at which the height of the liquid in the cone is increasing when the height of the liquid above the apex is 36 centimeters. So we're interested in the rate of change. So when we hear rate of change, we have to think differentiate. So we're interested in the rate at which the height of the liquid, so here's the liquid, and this is its current height in our diagram. We're interested in the rate at which the height of the liquid is increasing. So it's obviously going up. The height is going up because the liquid's going into it. So we're interested in the rate at which the height of the liquid in the cone is increasing. So the rate that it's increasing when the height of the liquid above the apex is 36 centimeters. So we're going to let r centimeters be the radius of the liquid and let h centimeters be its height. So what we've done here is we've taken our diagram, our cone, and we've cut out a right angled triangle. So if we were to draw a line straight down the middle of our cone, it would actually break this into a right angled triangle, so it would be perpendicular at the top. So this is 48, so this is 48. The radius is 20, so the top of our triangle is 20. So we're going to let r centimeters be the radius of the liquid. So this grey section is the liquid. So this r here is the radius of the liquid. And h is the height of the liquid, so this is h. We're going to let v centimeters cubed be the volume of the liquid. So we want dh dt. So we're interested in the rate at which the height of the liquid in the cone is increasing when the height of the liquid above the apex is 36 centimeters. So we're interested in the rate at which the height of the liquid is increasing with respect to time. So that means, i.e., that is find dh dt. So h being the height, so the rate of change of the height with respect to time t. So dh dt. So we want dh dt. What's given to us? Well, we were told in the question that the liquid is poured into the cone at a rate of 3 centimeters cubed per second. So we were given dv dt, which is the rate of change of the volume with respect to time. And we were told that this dv dt is 3 centimeters cubed per second. So by the chain rule, dh dt, which is what we want, is going to be dv dt multiplied by dh dt. Because this is what we were given, dv dt, and we somehow have to make this become dh dt. So we have to multiply by a numerator of dh, so that we get our numerator to be dh, and we multiply by a denominator of dv, so that those two dv's can cancel. And when they do, we're left with dh over dt, which is what we want. So we know what dv dt is, we were given that. We now need to work out dh dt and multiply them to get what we want. So we need to find dh dt. So we need to find this. We do this in two stages. First, we write v in terms of h only, so v being the volume. This requires that we write r in terms of h first. So the first thing we do was write r in terms of h, and the second thing we do is write v in terms of h. So we're going to use the idea of similar triangles, because we have a triangle and then we have a smaller triangle inside it, so they are both similar to each other. So that means that the angles are all the same, but the lengths are different. But the lengths are in the same proportion with each other. So by similar triangles, we have r over 20 equals h over 40. So r over 20, so r over 20, these are the corresponding sides, equals h over 48. So h over 48. So they're the corresponding sides. So r over 20 equals h over 48. Now we want to solve for r. So we're going to multiply both sides by 20. So we have r equals 20h over 48, which simplifies to 5h over 12. So now we have r in terms of h. We have r in terms of h. So or equals 5h over 12. We have or in terms of h. So next we need to write v in terms of h. So v being the volume. So the volume for a cone is a third pi r squared h. So you get this from your formula book. You don't need to learn this off. We know now that r can be rewritten as 5h over 12. And then we just multiply out the brackets. So 5h over 12 squared is 25h squared over 144. And then simplifying, we get 25 pi over 432 h cubed. So now we have v in terms of h. We have the volume in terms of h. So let's just have a look over that again. We need to find dh dv. So we need to find the rate of change of h with respect to the volume. So dh dt, differentiate h with respect to v. So we did this in two stages. The first thing we did was we wrote or in terms of h. So we did that using similar triangles. So we have or equals 5h over 12. The second thing we did was we wrote v, the volume, in terms of h. So we got the volume formula from our formula book. We swapped the or for 5h over 12 because that's what we got or equal to. And now we have the volume in terms of h. So there's only a h in the volume. So this is what we wanted. We didn't want an or in the volume formula. We only wanted a h. And this is ultimately because we need to find dh dv. So we want to differentiate h with respect to v. Now, in order to do that, in order to differentiate h with respect to v, we really want h equals something with v in it. But what we have at the moment is v equals something with h in it. But that's okay, because what we can do is we can invert this. So the main thing that you want to realize is that we needed dh dv in order to ultimately work out dh dt. So we just want to have some sort of an equation that only has h and v in it. And that's what we now have. Pi is okay, obviously, because pi is a number. It's not a variable. So secondly, by finding dv dh, we can invert to find dh dv, which is what we really want, which is equal to 1 over dv dh. So in the previous slide, we worked out that the volume in terms of h is 25 pi over 432 h cubed. So dv dh is going to be 25 pi over 432, so we take the constant outside, multiplied by 3h squared. So the derivative of h cubed is 3h squared. And simplifying, that gives us 25 pi over 144 h squared. So dh dv, which is what we really want, is going to be 1 over dv dh. So that's going to be 1 over 25 pi h squared over 144, which will give us 144 over 25 pi h squared. So this is what we really want. So going back to our chain rule now, we are looking for dh dt. So we're looking for the rate of change of the height with respect to time. And we know that we'll get that by getting dv dt and multiplying it by dh dv. So dv dt was given in the question as 3. So dv dt is the rate at which the liquid is being poured into the cone. So that's really dv dt, so dv being the rate of change of the volume with respect to t, the time. So dv dt is 3, so we put brackets around it, and dh dv is 144 over 25 pi h squared, which is what we worked out up here. And multiplying, we get 432 over 25 pi h squared. So dh dt, which is what we're really looking for, which is the rate at which the height of the liquid in the cone is increasing, is equal to 432 over 25 pi h squared. Now we were specifically asked of the rate when the height of the liquid above the apex is 36 centimeters. So what we do is let h equal 36. So we swap that h for 36. So dh dt is 432 over 25 pi times 36 squared, which gives us 1 over 75 centimeters per second, which is approximately equal to 0.00424 centimeters per second. So the rate at which the height of the liquid in the cone is increasing when the height of the liquid above the apex is 36 centimeters is approximately equal to 0.00424 centimeters per second. Example 2. A rope is attached to the bow of a boat A. So here we have the boat A. And here's the rope that's attached to it. And passes through B, a ring at the edge of the dock. So there's a ring here at the edge of the dock. So this is the dock. So here's the boat, here's the dock, and here is the rope attached. B is 4 meters vertically above A. So here's A, the height of A, which is here, and B is 4 meters higher than it. The boat is pulled in towards the dock by the rope at a rate of 0.1 meters per second. So the boat is being pulled inwards by the rope, which is being pulled upwards. And it is at a rate of 0.1 meters per second, i.e. the length of AB, so the distance between point A and point B, is decreasing, so getting less or getting smaller, at a rate of 0.1 meters per second. Determine how fast the boat is approaching the dock when AB, the distance between A and B, is 5 meters. So when there's any mention of increasing or decreasing rates and how fast, we want to think differentiate. So we're going to let AB, the distance between A and B, be x meters. So I've drawn this out separately down here. So the distance between A and B is x. Let y meters be the distance from A to the vertical dock wall. So we're going to let this distance here be y. So that's from the boat to the wall. So this is the dock wall. We want dy dt. So we want the rate of change of y, so the rate of change of the distance with respect to t. So with respect to time. So what's given to us? We were told that dx dt is equal to minus 0.1 meters per second. We've put in the minus here because we were told it was decreasing. So it's minus 0.1 meters per second. So we were given dx dt. So we were given the rate of change of the distance between A and B, or the length of the rope between A and B, with respect to time. So we want dy dt. We were given dx dt. So what are we going to multiply this by in order to get this? Well, we already have dt as our denominator, but we need dy as our numerator. So we're going to multiply it by a fraction that has a numerator of dy and that has a denominator of dx. Because multiplying these, the dx's will cancel. And we are left with dy over dt, which is what we want. So this is what we want. This is what we were given. So this is what we need to find next. So next we need to find dy dx. So the rate of change of y with respect to x. So to find dy dx, we will get y in terms of x. So we're going to use Pythagoras Theorem. This is going to be our right angle triangle. This is obviously going to be our right angle because this is a vertical wall. So this is our hypotenuse C, and that's x. We're going to label the 4 as b and the y as a. So using Pythagoras' theorem, c squared equals a squared plus b squared, we get y squared plus 4 squared equals x squared. So y is going to be the square root of x squared minus 16, which can be rewritten as x squared minus 16 to the power of a half. So now we have y in terms of x, which is what we wanted. So we're going to use the chain rule to work out dy dx. So we're going to differentiate x squared minus 16 to the power of a half. So we use the chain rule, we differentiate the outside, so we bring the power down in front, and we reduce the power by 1. A half minus 1 is minus a half. So we have a half times x squared minus 16 to the power of minus a half. So we've differentiated the outside. Now we differentiate the inside. The derivative of x squared is 2x, the derivative of minus 16 is 0. So now we multiply. A half times 2x is just x. And x squared minus 16 to the power of minus a half, well, the minus we can change to be 1 over, and 1 times x is just x. And to the power of a half, we can change to be the square root. So we end up with x over the square root of x squared minus 16. If you're finding this part tricky, you might want to have a look over our indices videos or our chain rule videos. So in our previous slide, we worked out that dy dx is x over the square root of x squared minus 16. So dy dt, which is what we're looking for, we're trying to determine how fast the boat is approaching. So if this is y, and we're interested in how fast the boat is getting in towards the dock, we're looking for dy dt. So the rate of change of y with respect to t. So dy dt, we know from the previous slide, is equal to dx dt multiplied by dy dx. We know that dx dt is minus a tenth. So we were told it was decreasing at a rate of 0.1. So therefore dx dt is minus 0.1, which is minus a tenth. And we worked out that dy dx is x over root x squared minus 16. So we got that in the previous slide. So then multiplying, we get minus x over 10 root x squared minus 16. Now we were specifically asked how fast the boat is approaching the dock when AB, the distance between A and B, is 5 meters. So we swap each of those x's for 5. So we get dy dt equals minus 5 over 10 root 25 minus 16, which gives us minus a sixth. I.e., that is, the boat is approaching the dock at 1/6 meters per second. An alternative approach to example 2 is to start with the equation y squared plus 4 squared equals x squared. So that's using Pythagoras' theorem. So here's our c, here's our a, and here's our b. Or y squared plus 16 equals x squared. Then we use implicit differentiation and the chain rule to differentiate both sides with respect to t. So we differentiate the y squared, so dy squared dt, differentiate the y squared with respect to t. So since we don't have a t, we just stick on a dy dt. So we're going to differentiate y squared with respect to y and then stick on a dy dt. And differentiating y squared with respect to y gives us 2y, and then we stick on the dy dt. Then we differentiate the 16 with respect to t, so that just gives us 0. And then on the right of the equal sign, we just differentiate the x squared with respect to t. So again, there's no t, so we're going to use the chain rule. So we're going to differentiate x squared with respect to x and stick on implicit differentiation, so stick on dx dt. So differentiating x squared with respect to x, we get 2x, and then we stick on the dx dt. So we have 2y dy dt equals 2x dx dt. So dividing across by 2y, we get the dy dt on its own. So dy dt comes down here. So then 2x divided by 2y, the 2's will cancel and just give us x over y, and that's stuck onto the dx dt. So we have dy dt equals x over y times dx dt. When x is equal to 5, y is equal to root 25 minus 16, which is 3. So the x is going to be 5 and the y is going to be 3. And we are given dx dt equal to minus 0.1, which is minus a tenth. So we swap x for 5, y for 3, and dx dt for minus 1 over 10. And multiplying, we get minus 1 over 6 meters per second, as we did before.